All right, we're going to take a look at some more in-depth look at exponential growth and decay, or just in general growth and decay in real life situations. So I'm going to do a couple models together, and then I'm going to have a few for you to try on your own to see if you can understand not just how to, on the graphing calculator, come up with the equations, but to really understand what the numbers and the values mean. Because if we have a model that we can't really articulate to other people what it stands for or what the representations are, it's really not very useful to us. So we really want to make sure we can look at that. So the data I have is about stopping distance, so being able to stop if you see something in the road ahead of you. So they talk about two different kinds of stopping distances. There's, first of all, the reaction distance, just that distance along the road that as you see something in front of you, you realize, oh geez, I better stop, I don't want to hit that dog, and how long that's going to take you on the road for that to happen. So there's a certain amount of time associated with that, like your reaction time, but what that time translates into is distance that you're still traveling. So while you're processing, while your brain's saying, oh, I should stop and apply the brake, there's a distance along the road associated with that. And then once you apply the brake, then we have what's called the braking distance. So how long will it actually take your car to stop in front of whatever that obstacle is. So this data, this chart, is representing that. So the blue part, as you see it, has to do with the reaction distance, they call that, or the thinking distance. How long does it take for you to, how long in distance on the road will it take you to stop? And then the red on the graph is the actual braking distance, so the actual distance on the road once you apply the brake for different miles per hour. So what I did, just to make life a little bit easier to keep the data straight, is I set up a table. So if you can take a moment to go ahead and fill in from the graph the different values. So the speeds, the reaction distances, that was the blue, and then the braking distances, that was the red on my chart. Yours I know isn't color coded. And then the total stopping distance, which they do give you, otherwise you can just total the reaction and the braking together. So go ahead and take a moment, stop the video, and fill in the information for us. Okay, so what I have then is just kind of that completed table, just to give us some structure. So what we're going to look at first is the relationship between the speed and the reaction distance. So what kind of relationship is going there? So our speeds are going up by 10. If you look at the reaction distances, we're going up by 3, up by 3, up by 3, then 1, then 5. So the end is a little bit wonky, but that's a good math term, by the way, wonky. But we're going up by 3 each time. That kind of sounds to me constant rate of change, going up by the same amount. Kind of sounds like linear to me. And if you think about it, if you're reacting, like the time it takes you to react is probably going to be the same, but incrementally it will go up. The faster you're going, the longer you're going to travel on the road for that same amount of time that you're thinking. Because if you're going faster, you're going to cover more ground. But it looks like it's a constant sort of thing. As I increase my miles per hour, the reaction distance increases at the same rate. So it's going up by the same amount each time. So I'm kind of thinking this is looking like this model might be linear, but let's take a look when we put it into our graphing calculator. So what I want you to do is go ahead and go into your stat menu. So we're going to stat, I'll kind of start from the beginning here, edit, and put your X's, which are the miles per hour, in list 1, and then put your reaction distances into list 2. So what we're going to try to do is graph the relationship between those two and see if we can determine for sure if this is in fact a linear situation. So once you have your data in there, you may have to pause the video. I'm going to have you go to your stat plot menu, make sure you turn your plot 1 on, and make sure your X's are in list 1, your Y's are in list 2, and then go ahead and go to your window. We're going to set up our window to be appropriate for our data. So for our speeds, what's the slowest speed we could ever be going? Well, 0. So I started at 0. And then our maximum that we went up to was 70. So I went a little bit beyond that. I went to 80. You can't be going slower than 0. That'd be negative speed. Going backwards, I don't know. This doesn't really make sense for our situation that we're looking at. For the Y's, we're looking at the braking distances, or the reaction distances first. So again, slow or smallest, shortest distance it could ever be would be 0. If you're not moving at all, or you react and you can instantaneously stop immediately as soon as you saw it, that would probably mean you're not moving, but that would be 0. We can't really have negative. Hey, I already stopped, did it before. Doesn't really make sense. All right, then the maximum looks like we went up to 21, so I'm going to go a little bit past that. Each set of data, you're going to have to adjust your window. Some people do a zoom fit. I kind of like to have control over my window, so when I'm thinking about what it means. So that's what I'm going to do. If you double check your y equals, make sure there's nothing in there, and then go ahead and graph, we should see our relationship. And, you know, I really am feeling pretty confident about that linear model because especially for those first 4 points, it looks very accurate. There's one kind of blip in there, but for by and large, most most of these are kind of in a good spot to be able to look for that constant rate of change. So let's talk about that model then. So we'll do this model. So when I say what is the model, I'm talking about what type of parent graph would best fit that. And I'm thinking it's linear. It sure looks like that's going to be a linear model, y equals mx plus b. So why are we choosing this model? That's what you're going to be thinking about for your data sets as well. I'm choosing that because it looks like there is a constant rate of change. So I'm going up by the same amount each time. So as I increase my miles per hour, my reacting distance is going up at a same amount each time. So a constant rate of change. So I definitely have that sort of appearance in the graph. So let's go ahead and have the calculator do our calculation for us. So I'm going to go to Stat and then over to Calculate. And now we want linear, so that's number 4. Now if you can store, you should definitely do that. So if you're going to store your data, that's where you go into like I know yours looks a little bit different, but go down to the 4th line. It says regression equations store. You go to vars and then over to yvars and then number 1 function, and then it will say y1 and all the different options. Choose y1. Then make sure you go back to your home screen, go down to calculate and press calculate. So what that does for you is it allows you to put your equation right into your y equals. For me, I'm going to have to do it the old-fashioned way, so I'm just going to be typing it in. Go ahead and round your equation to hundredths, so y equals 0.28x plus 0.44, and I'm going to go ahead and type that into my y equals. You guys, if you stored it, you are good to go. You don't have to worry about that. And then let's see how well it matches up. So I'm going to go ahead and hit graph and see how this looks. Looks pretty solid. So when I'm looking at that model, I'm feeling pretty good about how that looks. It's really matching up nicely. All right, so let's talk about what each of these things mean in this equation scenario. And this is the part that it's really critical for you to understand for when you do your own sets of data here. What do each of these values really tell you? All right, so let's talk them through. So the y value, the output, think about your graph. The output values, these are your distances for your thinking or reacting. So it's your reacting distance in meters. So when I talk about that for my graph now or for my equation, this is my reaction distance, and that is measured in meters. You really want to be specific with what the units are that you're measuring. Okay, how about the x value? Well, think about what the x's were. These were our speeds, right? Our 10, 20, 30, whatever, and those were in miles per hour. So this is speed versus reacting distance. In other words, our reaction distance is a function of or depends on our speed. So that means we have a linear relationship happening between those. So the speed in miles per hour. Okay, now let's talk about the m and the b. Now in your graphing calculator, they called the m a. It was the a value, but it's the same thing. It's the slope. So the slope in this equation is 0.28. Now slopes are rates of change. So rise over run. We have to think about what that means in this situation then. Y over x. Y is our reaction distance in meters per speed in miles per hour. So this rate that we're talking about, it's the reaction distance per miles per hour. So that means it's 0.28 meters for every mile per hour faster that we're traveling. So that means for every mile per hour you increase your speed, it is going to take another 0.28 meters along the road for you to recognize, oh shoot, I need to stop. So 0.28 of a meter, it's almost like a third of a meter. So think of like a meter stick, like a yardstick, it's a third of that. So that's every mile per hour faster you go, it'll be another almost third of a meter in that reaction distance. So it's a rate, it's the reaction distance per mile per hour. The b value just in the equation is 0.44. We need to talk about what that is though. In slope-intercept form, this was the slope. This is the y-intercept. So what that's representing is when we're on the y-axis. That means when x is 0. And what does x mean again? The speed. So this is the y value, which is reaction distance. So this is the reaction distance when x is 0, which means when we're traveling 0 miles per hour. So this would have to be in meters then because it's a y value. It's an output. So what this is saying is our reaction distance is 0.44 of a meter when we're going 0 miles per hour. Now let's think about that. If you're going 0 miles per hour, You're not moving. So you can't have a reaction distance if you're not moving. So why is this happening? Well, this is a best fit equation, remember. When you look at your graphing calculator, this is fitting all of the points. It's not going to be actually perfect in theory of what we know to be true. So I know it's supposed to be 0 because I'm not moving, but our best fit to fit all those other points, it's going to be off a little bit. So don't be surprised by that. These are models. There's things that we need to do in interpreting that to make sense with that. So I'm going to have you look ahead then and do this first prediction then. So using your model, I want you to predict the thinking or reacting distance if you're traveling at 100 miles per hour. Well, there's two different ways you can really do that, and I want you to do both. One way is to just use our equation, our rounded equation. So we can use our y equals 0.28 x, but now our x would be 100, and do our calculation. So for x equals 100 in the equation, we can come up with our prediction. So go ahead and do that and see what you come up with. So you can pause the video if you need to. And I got 28.44 meters. Now our other option though, if you think about it, we could just look in our table. You've already stored that equation, right? So if you look at your x equals 100, standing for 100 miles per hour, we could just look in our table and find that x equals 100. Now remember, if you're going to your table, I would not like just go to the table and say, oh look, I'm going to have to arrow down. I'm totally in the wrong spot. I would go to my table set and then start it at 100, so then it's a lot easier to be able to go and do that. And then you can get right to that value. So if you look it up in your table and you've stored the actual full equation, the y value that I came up with was 28.724, and that would also be in meters. Now let's look at that comparison. They're not identical, and why is that? Well, the equation was rounded. My stored equation was all the decimal values. So there's going to be a little bit of difference, but for linear, it's not that big of a deal. They're pretty close because we're only going up by the same amount each time. Add something, add something, add something. It's not as big of a deal. Now think about what that means though. Your actual reacting distance on the road, if you're going 100 miles per hour, is 28, almost 29 meters. Think of a meter stick. It's like the length of at least a couple classrooms. So it's a long distance at going 100 miles per hour. That's just you thinking about it, how long that's going to distance on the road that would be. So that is your reacting distance at 100 miles per hour. Okay, now let's go back and take a look at the other model. I want to compare this, and this is kind of interesting. I want you to go back now and do braking distance. So we're going to look at that graph instead. So let's talk about the braking distance. So when we look at, instead, go to your stat edit and put in braking distance for your list 2, the relationship is very different, and that's kind of interesting because you feel like it should be the same. Same kind of situation, but in fact, the length of time it takes to brake increases much more rapidly. The distance between them is not the same, like it was up by 3, up by 3, up by 3 for reacting. Braking, it's up by 8, and then by 10, and then even more. So as we go up, it gets even greater. I'm going to go ahead and clear out my old equations. I want to make sure I clear that out. My stat plot's already turned on. I'm going to adjust, though, because my braking distance, the miles per hour is fine, but my braking distance is a lot further. So I'm going to go up even larger here. So we're going to go up a little bit further. So I'm going to go up to, say, 80 to get to that 75, and then go ahead and take a look and see what the graph looks like. All right, so in terms of a model, this is definitely, to me, looking a lot more like an exponential. The distance between those points seems to be growing, increasing. It's not a constant rate of change. It continues to get bigger each time. So for me, I think that's a pretty good argument. The other thing that these kind of graphs have that linear equations don't is an asymptote. So kind of the two things that we might think that make something exponential to be able to talk about that model or to choose that model is the fact that our graph, number one, it curves a little bit. That distance between the points continues to increase. That's a percent increase then. It's not a constant rate of change, so it's a percent increase between those values. But the other thing is, think about what exponential graphs do. They approach asymptotes, either whether you're increasing or decreasing, it doesn't matter. One end of the graph is approaching an asymptote. So the other part of why I think we can argue that is it definitely looks like it's curving down towards 0. It looks like it's approaching 0 because you're going to be getting closer and closer to that 0 time and 0 speed, and that would be 0 distance then. So we can definitely, I think, argue that. So it's curving, the distance between those points is increasing, and we can argue that asymptote. All right, so let's have the calculator calculate that one. So we're going to go over to stat calculate. Now it's 0. Go ahead and store if you can. Whoa, that is not what I wanted. Go ahead and store it if you would like to, so you can get that into your y equals. I'm going to do it the old-fashioned way here. Go ahead and round to hundredths again for your equation. So y equals 2.83 times 1.05 to the x. So exponential equation, I'm going to go ahead and type that into my y equals so I can see how well that fits before we start talking about what each of those numbers represent to the x. Okay, so if you've stored it, you're good. And then we can see how well it fits. Surprisingly, I think actually this looks pretty good. When we think about what that model is going to look like, it actually is pretty decent. So some are above, some are below, but I feel like it really does fit that situation pretty well. All right, so let's take a peek at what each of these values is going to look like then. All right, so let's go through and talk about what each of these values would mean then in this model, since it fits pretty well. So we're going to talk about our y and our x. So in this case, our y, our output, we're looking at braking distance this time. So it's our braking distance. And then our x value would be the speed again. So speed in miles per hour. And then braking distance would be in meters. Probably the trickier part, though, is what are the A and the B representing. So let's talk about the B first, the base, this 1.05. The base being 1.05 in exponential means since it's bigger than 1, it's growth, and it's growing at 5%. So it's 5% growth. Now, this nice nebulous word, it is growing. What is it? It's the output is growing. Our output, which is the braking distance, our y. So the braking distance is growing 5% every 1 mile per hour that you increase your speed. Because remember, this is a rate. It's a rate of growth. So it's the braking distance per mile per hour that you are traveling. So every mile per hour you travel faster, you've increased your braking distance by 5% over what it was previously. So the braking distance per mile per hour, so that you increase. So this is definitely going to be significant, 5% more each time. Okay, the A value, the out front. So the number part itself is 2.83. Okay, so what does that mean? Well, that's our initial value. When you think about it for an exponential equation, what's ever out front is kind of your starting value. It's your y-intercept. So when x is 0 again, if you put in 0, anything to the 0 power is 1. 1 times 2.83 would be 2.83, which means the y value would be 2.83. That's your braking distance. So that's in meters. So what does that all mean? Well, at x equals 0, that means 0 miles per hour. Your braking distance would be 2.83 meters. Okay, let's think about that. If you're traveling 0 miles per hour, will your braking distance be anything more than 0? Well, it shouldn't be in the real situation, but for our best fit equation, that's not going to be able to be 0. If the A value was 0, our equation becomes very uninteresting. It would be y equals 0. It would be a horizontal line. We're not moving. So we know that this has to have a value to have the model, but in reality, we do know if we're not moving, we don't have a braking distance either. All right, so let's do that projection then for that second piece. So I want to take a look at what that would be for braking distance for our model. So again, we're going to do it 2 different ways. We're going to use our equation. So just by substituting in our x equals 100 miles per hour, what would our braking distance look like? So we'd have 2.83 times 1.05 to the 100th power. And when you do that with your equation, go ahead, pause the video, calculate that. And then the other way I'd like you to do it is by your table. So you should have stored your equation in there. So we're looking at x equals 100 and finding our y value. Okay, so let's compare those. Go ahead, pause the video, get your 2 numbers. For my equation, I got 372.15 in meters. And then by my table with the stored equation, I got 402.43 meters. And this is the braking distance now for 100 miles per hour. Okay, that's crazy. Think about like the 400 meter. If you're a track runner, 400 meters is a long ways if you're running the 400 meter. So that's the distances we're talking about. Now look at how different they are though. The difference of the rounded equation versus the table with all the decimal values. So obviously all the decimal values is more accurate. So when we round, we definitely have an issue. But in the linear one, it wasn't nearly so pronounced. Why is it so much more for exponential? Well, what do you do in an exponential equation? You multiply by something, right? And now we've done it 100 times, right, to the 100th power. That's going to be a lot of error when we think about that rounding. So I'm using that rounded number 100 times. So that's why it's going to be a little bit off. Either way, though, it's a pretty significant distance for stopping or for braking. So could you figure out your total stopping distance then? Well, you'd have to add your reacting with your braking. You're looking at somewhere between 400 and 430 meters to be able to stop when you're traveling 100 miles an hour. So it is definitely a consideration. That's why I always talk about don't get too close, don't speed. You need to have that time to be able to stop. Okay, so what you're going to do then is there are 3 more sets of data for you to look at. So there's an example 1, 2, and 3. I'm going to have you go through and enter the data, list what your X, Y, A, and B stand for these exponential models. Talk about why you chose this model. Again, those 2 reasons, the idea of the percent increase and then the asymptote, those 2 possibilities. And then you're going to do some projections for each of them. You're going to answer some questions about that data set.